Good evening, you all. Let's start the session for today. So, I welcome you all for this live session, third live session in numerical methods for engineers. Uh, I myself is Rigved Samant. I am a PhD student at IIT Guwahati, and I'm working on the field of lithium-ion batteries and studying its behavior and trying to predict the fault detection mechanism for lithium-ion failures. So while doing that, I am using some mathematical models, and to solve those mathematical models, I'm basically using numerical techniques. So that knowledge would have been helpful for you pertaining to this course. Yeah. So what I was saying is, I was welcoming you all to this session, and let's get started. So this is the third live session. So people who have missed the first two sessions, they can go on to the YouTube link, which is provided in your Swayam portal. So if you go on your Swayam portal, to the left hand side, at the last there would be a tab called Problem Solving Session. If you go inside, there would be a link for opening and if you open that link, you will get a spreadsheet. In that spreadsheet, there would be a link for each sessions that I have undertaken for the last 2 weeks. So all the videos are going to be get uploaded on the YouTube channel pertaining to this course itself. So if you guys don't have a time at the time slot it is going to get live, you can always access that at your own pace. But we encourage you all to come to this live session. So without further ado, let's get started with the third session. So in the previous session, we had started with the linear system of equations. So in the linear system, professor had started with what is basics of linear algebra. After basics of linear algebra, he started with he discussed the brief about what is line representation. I mean, if you have two unknowns, then it can be shown as a line. If you have three unknowns and three equations, and then it can be a system of planes, and we talked about that. Then if you have a system of linear systems, simultaneous equations, then it can be written down as a augmented B matrix, where A is your coefficients of your left hand side and B is the vector of the right hand side. And this A augmented matrix, if you can find its rank, then you can understand talk about how many nature of the solution for that particular system. We talked about that. After doing that, we studied how to get the solution of these equations. So there is one method called the determinant. By determinant, that I mean by Cramer's rule. By Cramer's rule, we saw how to get it. Then we saw using a Gauss elimination method. So it was a naive Gauss elimination method where we just take if we have a A11, A12, A13, A21, A22, A23, A31, A32, A33. With Gauss elimination, what we do, we take this. So this is your A matrix. We take this a pivot. So these diagonal elements are your pivot elements, or diagonal elements. Using this diagonal element, we make this 0, then using this diagonal element, in the next step we make this 0. and then you do back substitution to get the values of x, y, z, or x1, x2, x3, or whatever the system you have. So this is a basic procedure of a Gauss elimination, where we didn't consider, we just made the zero without checking what are the pivot elements are. We just did without checking what are the values of pivot elements are. We just did just went with the procedure. Then there is another method called Gauss-Jordan method. In Gauss-Jordan method, we made in Gauss-Jordan method, this 1, 2, and 3 we made is equal to 1, and with that, and this was 0. So just because of that, what happens is when you get the final, so what happens is in Gauss-Jordan, at the last step you will get this all will be 0. So this will be 0, this will be 0, and you will only have this three or whatever system you have. If you have a 3 equations in 3 unknowns, you will have this kind of identity matrix, and with that you don't have to, and this will be x, y, z, and there will be a B matrix here, right? So directly we will get the values of x, y, z, or x1, x2, x3 without doing a back substitution. So that was about Gauss-Jordan method. After Gauss-Jordan, we also saw another technique called LU decomposition. So LU decomposition is, after you complete your this normal Gauss elimination, you end up with A11, some A12, A13, 0, A21, A23, 0, A2, A0, 0, A3, 3, right? So this is your upper triangular matrix, and the coefficients you use, this is your upper triangular matrix U, and there is a other matrix as a lower triangular matrix with your diagonal elements and your alpha 2, alpha 1, 2, alpha 2, 1, and alpha 2, 3. So this will give you a decomposition which can use to find out the inverse of a matrix. So this is what we saw in the last class, and then we took some numericals. So this was a quick recap of what we did in the last week. In this week, if you have gone through the lectures, we completed Gauss elimination with the partial pivoting. So what is a partial pivoting? Let's say you have this A11, A12, A13, A21, A22, A23, A31, A32, A33. Okay. So if I wanted to make a 0 here, what I did 0. So in normal Gauss elimination, using this A11, I made 0 here, right, and 0 here. In partial pivoting, what I will do is I will check what in A11, A21, and A31, that is the first column, which is the highest element in respect of the magnitude. We don't bother about is negative or the positive sign, just the magnitude of it, which is the highest, and that row would be considered would be taken as the first row. So if the A21 is the highest element, we will swap R1 to the R2, so that this will go here and this will come here. So we'll see how to do that. And why it is a partial pivoting? Because we are just swapping rows here. We are not considered about what's happening. We are not checking what is relation between these columns. Columns, we are not changing its order. We are just changing the order of the rows. That is why it's a partial pivoting. Complete pivoting means you also check the order of the columns also. So we'll see from numericals how to do that. Then tridiagonal matrix algorithm or a Thomas algorithm. So what happens is, because of the system of whatever the engineering problem you have, once you try to solve it using differential equations in the time, so for a one time period there would be a one differential equation. At the next time step there would be one differential equation. So because of that there would be a simultaneous differential equation, and that differential equations can be solved as a simultaneous equations that we will see in the next modules. In the ODE chapter we will get to know that. So it gives you a matrix such as you will have a diagonal element, a super diagonal element and a sub diagonal element, and rest of the element to be 0. So these elements so what I was saying, we will get a diagonal, super diagonal and a sub diagonal element, and the rest of the things are 0. In this case, rather than going for a Gauss elimination method, it's better to use a Thomas algorithm, which will reduce your computational cost, or it will lead to the answer in the fast manner. So it depends on what the nature of your problem is. Then these all, so Gauss elimination, Cramer's rule, Gauss-Jordan method, and LU decomposition, and even your Thomas algorithm and Gauss elimination without partial pivoting are all your direct methods. So here you are not iterating on the solution you get. You whatever you get at the first step, you consider it as a final solution. In the iterative method, we iterate over a set of equations again and again and get to the final solution. So we will see through the problem what is a Gauss Siedel and what is a Jacobi and what is the difference between these two. So without a further ado, let's get started with the question set for the today. So yeah, so the first question is for the linear system 0.0003 plus x plus 3y is equal to 2.000001 and 1 x plus y is equal to 1. Find the values of x and y using Gauss elimination with partial pivoting and Gauss elimination without partial pivoting. Use round off till 4 decimal places to compute the solution. So how you will go about this? First you will write a augmented B matrix, right? So what will the A augmented B matrix? So let's first, what is A is? A is Gauss elimination with partial pivoting, right? So what is your A augmented B matrix? A augmented B matrix is 0.0003 2.001 1 1 1, right? So what is a partial pivoting? What we have to do here?
No idea, sir.
Yes, sir.
No idea.
You went through the lectures?
I seen, but not observed that.
Okay. So we'll do that here. So what are the pivots? Did you understand what are pivot? You go for partial pivoting later. What are the pivot? What is a pivot mean by?
Diagonal elements?
Yes. So for this first row, the diagonal element is this. So this is a pivot element pertaining to the row 1. This is a diagonal element pertaining to the row 2. Pivot for row 2. Okay. So these two are your pivot elements. Okay. At the first step, you are only concerned with this element. Okay. This first pivot row, pivot of the first row. In normal Gauss elimination, what you did, using this one, using this pivot, you made this 0, right? So how you did that? R2 would be R2 minus 1 divided by 0.003 R1. So this will become 0. You yes sir, just let me get back my setup and then we'll start. So in naive Gauss elimination, what I was saying, sir, you are able to hear me, right? Hello.
Sir.
Yes. So in naive Gauss elimination, what we did is we made this. We took the first pivot element of the row 1 and we made whatever the values beyond this, below the first row element, first column, this pivot element 0. So using this we made this 0. So how we did is R2 minus 1, this 1 divided by 0.33 is equal to 1. So this will become 0 and rest of the things will be happen in that order. But what the problem with this is, we'll see this, we are going to solve using without a partial pivoting also. We'll see what the problem would be. So rather than doing that, what we'll do in the partial pivoting is we will check. So for the first step we are only concerned with the first column, right? We are only concerned with the first column, this one and this one. So in between these two we will see which is having the highest value, this absolute value. So this is value is a 0.003. So since one is greater than, so in normal, so in partial pivoting what we will do is, for the first step we are concerned with the first pivot element of the first row, that is this one. In that respective column we will check which is having the highest magnitude. So 0.0003 is less than 1 implies R2 should be swapped with R1 because it has a highest value that this one will take at a pivot element. So this one will take it at a pivot element. So R2 is swapped with R1. So it will become 1, 1, 1, 0.0003, 3, 2.001. Sir, you understood why we changed? Because the one's magnitude is higher than 0.003 that we do in the partial pivoting. So pivot element was at this one. This one was a pivot element for the first row, first step, and we checked its column at the highest value we saw and accordingly we shifted it. Now with this one we'll have to make this 0, right? So using this one we have to make this value 0. So it is straightforward, right? How will you do that? R2 would be, what will be that value? Sir?
R2 dash is R2 minus 0.003 into R1.
R2 minus 0.003
into R1.
Yeah. So this will be 0. I'll get my calculator. So what you get? 2.997, right?
Yes, right.
And here you will get 1.9998,
Okay.
right? So here are first this not iteration, first step is over. Now we made this 0, so now we will move on to the next pivot element, this one. But below this there is nothing, right? So basically our procedure is stopped here. From, if there would have been some value below this, then we would have to use it, we would have had to compare between this value and the value below that. The highest one row would come at a second. If this would have been the highest value, it would have stayed as it is. Okay. So now from here you can calculate the value of what it is y, right? So what will be the y? Y would be 1.9998 divided by 2.9997. That is 0.6667, right? And the first row would give you x is equal to 1 minus 0.6667, right? That is 0.3333.
Okay.
So we got x and y value. Okay. So let's solve using, so a part is over, second part is without partial pivoting. So that's what we did in first, that is nothing but a naive. In the previous class, whatever we did. So what is the this thing 0.3, 3.1 and 111. So A augmented B would be 0.0003 3 2.001 3 2.0001 111, correct? So it's naive. So in naive, what we do, we using this element we make this 0. So R2 would be minus 1 divided by 0.0003 R1. So this is 0.0003 3 2.001. this will become 0. So 1 minus 1 divided by 0.0003 into R1 is 3. This would be minus 9999, and the second one would be 1 minus 2 2.00. This is minus 6666. Correct? Correct, right? So we'll find, so below this there is nothing, so our Gauss elimination stops here, and we'll be doing back substitution. So with back substitution we get is y is equal to minus 999, sorry, minus 4 times 6 divided by minus 4 times 9. So that is nothing but 1 divided by 3, that is 0.6667. The answer is matching for x or y. Now let's find x. X is 0.0003x plus 3y is equal to 2.001. That is from equation 1, right? So what would be x? X would be 2.0001 minus 3 into 0.6667 divided by 0.0003. So what is the value of x?
Zero.
0, right? So x is coming out to be 0 here. And what is x?
0.333.
0.333. There is a method to find it in this this thing also, you know, right? So you can Google it. I mean, if you go into this option, equation option, and you put the and you select simultaneous equation as 1, then he will ask you what is the number of unknowns, and then it will give you basically this a augmented b here only, and you put the values of those coefficients and it will give you answer. So 0.0003 So see, when I put it, it will give me 2.3 as y, and if I can move around, then it will give me x also.
1 by 3.
2 by 3, 1 by 3. So these are the actual values which we got from partial pivoting. Okay, so partial pivoting is giving you a correct answer, but without partial pivoting you are getting a 0 here. Can you tell me why? Yes, we actually have looked it in the first class. If you can recall the lecture 1 session 1, live session 1, in that I told you something about being cautious with numerical methods. Can you see it?
Forgot, not remember.
So always remember, while doing these numerical methods, we have to take care of when there is a negative sign or then there is a division. So if you see this value 2.0001 and 3 into this is 0.67 is a 2 by 3, so 3. So it's basically 2.0001 minus 2, right? And 0.0003. So it's basically cancelling each other out here. So while doing this kind of a study, you will always have to be sure that you are not, when that is why you are using the partial pivoting. In partial pivoting, this problem gets eradicated. So that is why partial pivoting is effective when you are working with the values which are very close to each other. So when it comes to ill-conditioned system, you have to use these kind of things. So in the when there is the values are large, I mean there is a difference between the value is very large, that time normal Gauss elimination would work fine. But partial pivoting gives you more robustness in terms of numerical techniques. So that is why we have to use the partial pivoting. So partial pivoting, what partial pivoting is, we will check the column of that respective pivot element and select the row with which the pivot element having the highest value as our pivot point. So here what happened is the row 2 had the highest value, so we swapped it first and then we carry forward the Gauss elimination technique. So that is about your first question, Gauss elimination without partial pivoting and with partial pivoting and why to use it. Then second question is, consider this system of equation about tridiagonal system using a Thomas method. So tridiagonal system. So tridiagonal system means, let's see what kind of a system this comes out to be. So if you find out the A augmented, sorry, blue and I will use solution. So A augmented B. So what is A augmented B here? 3 minus 1, 0, there is no Z, so 0, 6, 1, 2, 1 minus 4, X is not there, 0, minus 1, minus 3, 0, right? So if you see, right, this element is here, this element is here, and third one, this element is here, right? So this kind of a system is called as a tridiagonal system. In this system we use Thomas algorithm, which is nothing but modified Gauss elimination only, which reduces your computation cost. So what we will do first is, in this one, like Gauss Jordan, we will make the pivot element 1. So first we'll check this thing for this one, right? This is having the highest value, so basically this is the one we are going to use as a 3. Now using we will have to make it as a 1. So what will be our step? R1 would be R1 divided by 3, since Thomas. Okay, so it will be 1 minus 1 by 3, 0, 2, 1, 2, 1 minus 4, 0, minus 1, minus 3, 0. Right? Now rest is similar, using this pivot element, make this 0 and make this 0. in Thomas algorithm this will always be 0, so you just have to do this calculation and this calculation. Because of this 0, this value will not change, and you have to do changes for this equation. So basically what we will do is we will make this to be 0 and rest of the things will follow along. So R2 would be what will be the R2? R2 minus, we have to make that 0, so R2 minus using this pivot, so R2 minus R1. So 1 minus 1 by 3, 0, 2. This will become 0. 2 minus plus, sorry,
5 by 3.
how much? 7 by 3, right?
5 by 3? Oh, minus R. Okay. 7 by 3.
7 by 3. This would be 1 because it will not change. Anything in minus 0 is that value only. And this would be minus 6. Third row will not change. 0, minus 1, minus 3, 0. Okay. So we are done with the first column. Now our focus shifts on second pivot element, that is this one. So in Thomas algorithm, first we will make this equal to 1. Okay. So that what Thomas algorithm says. So R2 would be R2 divided by 7 by 3 is nothing but R2 3R2 divided by 7, right? 3R2 divided by 7. So first row would be similar, 1 minus 1 by 3, 0, 0, 2. This will be similar, this will be 1. So 1 into 3 by 7 is 3 by 7 minus 6 into 3 side, so 18 divided by 7 minus 18 divided by 7. This row will be same. The next step, what we will do, using this pivot, we will make this 0. So what will the operation? R2, sorry, R3 would be R3 plus R2. So that will become 0, right? So what we get is 1 minus 1 by 3, 0, 2, 0, 1, 3 by 7 minus 18 by 7. Zero, 0. What we will get here? Minus 18 by 7. Is it correct?
Yes.
Yes, right.
This is right.
So for this third diagonal element, there is nothing here. So our algorithm stops here. Okay. So we will have to just do back substitution. Back substitution we have to do.
Sir, can you do before going back substitution? You can divide R3 is minus 17 by 18 because you can make it to 1. You can use it to get the solution also, no?
So you are saying that because of this.
It is simplified.
So that's what
Almost
you're doing in substitution. So it's anyway
We
you're
are
doing
done.
here or there, it's anyway same, right?
because here the fraction is there, make it in the fraction 1.
So
1.
yeah, always you can do that. Divide by this thing, so you will get -1. You will get 1 and 1 here.
That is easy
That
to
is also you
substitution.
can do. Yeah, in Thomas algorithm you can do that because that is a step there. But because since there is nothing below that, we don't generally do it in the computation. So
But there is no any variation of answer.
Yeah, there will be no variation also. So what will be the so Z would be 1, right?
Okay.
0. Let me just check this value again. R3 plus R2, huh? 0 minus it, yeah, and -3 plus 3 by 7. Yeah, correct. Z will be 1. Y would be -18 divided by 7 minus 3 by 7. So -21 by 7, that is -3. And X would be 2 plus 1 by 3 into -3 minus 1. So this is -1. How much? Sorry, here it would be 0, right? There is nothing here. This is 0. Okay.
Sir, actually in assignment they given in the place of x and y z, they take it as t1, tia minus 1, tia plus 1, and 51 like that for tri-diagonal matrix. Thomas algorithm.
Yeah, that is t plus 1, that is a different times. So you consider them as a different variables, right?
In the place of x and y z, they give it as, but it is related to, that is, terms is always ti and ta minus 1, ta plus 1, means prefix suffix.
Okay.
Like that.
So maybe I'll just check once what is the.
That is problem number 4.
So
Setting up tri-diagonal matrix, that related problem, using Thomas algorithm. (51) linear equation in tri-diagonal form.
yeah.
This method is related good for either problem number 5, sir, or problem number 4.
This is Thomas algorithm only for tri-diagonal matrix.
Means that is problem number 5 in the assignment. Easy to solve.
Yeah.
But not problem number 4.
The problem number 4 is not just you have to set up the this thing. So you just have to make this A augmented B matrix using the equations and whatever it is given there. So you have to write the first one would be T1 minus 250. So T1 is equal to minus 250. T1 is equal to 250. So value of A would be straightforward, because actually we have been specifically told don't discuss these problems. So after you get any, so in this one, what I can do is you have to, according to this, what we have, you wrote this one, right?
Hmm.
Similarly, consider T1, T2, T3 as equivalent to X, Y, Z, and so on. I mean, X1, X2, X3, X4, whatever. And so, what is the basic thing is, okay, I'll just give you A11, A12, A13, A21, A22, A23, A31, A32, A33, okay, into X1, X2, X3. That's what is there, okay. And then there would be P, Q, R. How we got about this? When we write the equation, how it is comes a11 into x1, a11, a12 into x2, a13 into x3 is equal to p. A21 into x1, a21 into x1, a22 into x2, a23 into x3 plus a22 into x2 plus a23 into x3 will be equal to q. A31 into x1, a32 into x2 and a33 into x3 is equal to r. So these are the equations there. So somewhere if I have only a11 x1 is equal to p, let's say. So what would be there? 1 0 0, rest I will write later, and this x1 x2 x3 whatever, and then here would be your p. So when you write this a augmented b, it would be 1 0 0 dot p, rest of the things accordingly, right? So that's what you have to do in that question number 4. Consider this x1 x2 x3 as t1 t2 t3 and write it.
Okay.
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 So I have to get that thing also, right? So yeah, maybe okay. So just try to solve this problem. I will get back to you, okay? In Gauss Siedel method. Okay, were you able to solve this?
No, sir.
Gauss Siedel method. So till now we saw all the direct methods. This is related to iterative method, Gauss Siedel and Jacobi.
Okay.
So in iterative method you will have a one equation and you iterate over again and again and again till you get the final solution. Okay. So here what is the thing is, first is Gauss Siedel method. Okay. Now solution using Gauss Siedel. So first you will write A augmented B, four 1 minus 1 1 minus 2 5 0 minus 7 2 1 6 13. Is it correct?
Yes, sir. Yes, right.
Is it diagonally dominated? So there is a condition of a diagonal dominance.
It is 4 is there, it is higher the number than the rest of the number of the diagonal.
So diagonal dominance is not it is a different in that one. We just see the absolute value of each, and whatever the value higher we swap the rows. Here what it is, we will see the diagonal element, that is 4, and will do addition of the rest of the element in that column. Okay, if that addition here is 2 minus 2, so it is 0, so it is higher than that, so we'll keep that one. Okay, for here also it is 5, 1 plus 1 is equal to 2, it is higher. Here also 6, this is minus 1 plus 0, that is 1, this is higher. So it is already diagonally dominated. Why to do that we'll see later. Okay. So we have to solve this. So after giving it the diagonal dominated, your first equation, let's say this is equation 1, this is equation 2, and this is equation 3. Your equation 1 will give you the equation for x. So first equation is what? 4x1 plus y minus z is equal to 1, right? From which you can write x is equal to 1 minus y plus z divided by 4. This is your equation for x. Equation 2 you will rewrite in terms of y. So equation 2 is 2x plus 5y is equal to minus 7. That is y is equal to minus 7 minus 5y divided by minus 2. Sorry, 5y we are keeping, y we are writing in terms of y, right? So minus 7 plus 2x divided by 5. Equation 2 will give you the equation of phi, and equation 3 will obviously give you equation of z. So last equation is what? 2x plus y plus 6z is equal to 13. So z is equal to 13 minus y minus 2x divided by 6. So these are your three equations. And you have been given initial guess as 0, 1, 1. x0 is 0, y0 is equal to 1, z0 is equal to also 1. Okay. So for Gauss Siedel, iteration 1, you will find x it's the first iteration. So 1, so we'll put value of y here and z here. So y 1 minus 1 plus 1 divided by 4. So that is 0.25. In x, sorry, x is done, right? Now y. First, after first iteration, y would be, you will use this x1 and the, so minus 7 plus 2 into x would be this x1. So x1 is 0.25 divided by 5. So how much is that? Minus 0.94. Sorry, minus 1.3. Yeah. And z1 you will use this y and this x to find z1. So 13 minus 1.3 minus 2 into 0.25 divided by 6. You will get 2.3. This is after first iteration. If you go into this and try to find the value of x, y, z, your actual values are x is equal to 1, y is equal to minus 1, z is equal to 2. They are far off. Let's say we don't know these values and let's just find out the relative error. So what is relative error? Ax after first iteration, epsilon x after first iteration. So what is that? 0.25 minus 0 divided by 0.25, that is equal to 1, right? Absolute of this. Epsilon y of 1, what is the value? 1 minus 1.3. What is the previous value was? 1 divided by current value. $1.769. Epsilon z 1 is equal to, what is the current value? 2.3 minus what was
Sir,
that?
you're calculating absolute error or relative error, sir?
Relative error, epsilon.
Okay.
In both cases you will have to take the mod only. With relative error divided by the current value.
For the relative error, but absolute error is not dividing.
Yeah.
Okay.
Divided by which value? 2.3. So 1.3 to 0.5652. Okay, so these are relatively very high errors, right? So if you go into percent, this is very high error,
More than 100.
more than 100, and this is 56% error. So we'll have to repeat it again and again and again. So let's go for iteration 2 and let's just see what happens. Iteration 2 would be Jacobi method, right? So Jacobi method will always consider the latest value. So x of 2 is, the equation is this one, 1 minus y plus z divided by 4. So 1 minus y1 would you consider? Minus 1.3. It's 1.3. Plus z. Z is what? 2.3. Z is 2.3. Divided by 4, right? Divided by 4. This would be 1.15.
This is Gauss Siedel, sir, or Jacobi?
This is Gauss Siedel.
Okay, right.
This is Gauss Siedel. In Gauss Siedel, what we do is we will always use whatever the latest value of the particular variable we have. So in first step we had only x, y and z. So we use this y, z naught. From that we got this x value. Now for a y of 1 we had x value, new x value, right? We use this here. And then we got y1. Now x and y we have, from that we got z. Rather in z we didn't use these two values. Okay. So for y2 you will use, y2 is minus 7 plus 2 into minus 2 into x. Now you have a x1. x1 is what? 0.25. So you will get 0.25 divided by 5. That is minus 0.94. Z2 would be thirteen minus y minus 2x. Y we have minus 0.94 minus 2 into x is what? 1.15 divided by 6, right? 6. Here 6. So what is the value here? 2.71.
More than 100%.
No, these are the actual values that we get in the next iteration. Now, if you consider the absolute error after second iteration, that is 1.15 minus first one was what? X was 0.25, right? 0.25 divided by 1.15. 1.15 minus 0.25 divided by 1.15 is equal to 0.7826. Similarly, 2 would be minus 0.94 minus this 1.3 minus 1.3 divided by minus 1.3. Sorry, divided by minus 0.94. Is 0.329. is what? 2.71 minus previous z value is 2.3 divided by 2.71. 0.0073. So the error is reducing, right? It was in more than 100, now it is 70, 38%, 7%, right? And if what was the actual values? 1 minus 1 2, that we know. And first one was this guess, and now first one was this values, which are far off from this, right? After first iteration. After second iteration, they are much closer. So 1, x is equal to 1, sorry, x is equal to 1, y is equal to minus 1, z is equal to 2. So they are reaching nearby, right? So if you continue this process over another iterations, you will find out the final values. So rather than doing this, I have made an Excel sheet for the illustration purpose for you. We'll see that. Where is it? Okay. So this is what it is. So if you see here, I'm not being able to. So for, if you see for the iteration number 1, how to draw, yeah. So for iteration number 1, why is it not? So if you see for iteration number 1, we got this 0.25, 0.1.3, and these were our epsilon values here, epsilon, epsilon, epsilon x. So as we go on with the iterations, right, this value is converging. So epsilon values are reducing here, and once we go below 10 raised to minus 3, we are nearby our actual solution at the 5th iteration itself. Okay. And if you go any further, at the 10th iteration, actually we got the integer values also. The error goes down significantly, right? So this is what a Gauss Siedel method, because of the diagonal dominance. Before going to before going to Jacobi method, let's just see if we had our equations like this. So if we had this a to minus, so what we had this set like 4 minus 2, right? Rather than this, if we had a augmented b as minus 2, so how was it? Let me just see. Minus 2x plus 5y. So minus 2x plus 5y would come out to be 5, 0 is equal to minus 7. Then 2x plus 5 plus 6 is equal to 13. 6 is equal to 13, and 4 1 minus 1 is equal to 1. If we had this, right, if we had this is diagonally dominated?
No.
So first one is minus 2, right?
Yes.
So it is less than this 4 plus 2. Now this 1 is less than 5 plus 1. This minus 1 is less than 6 plus 0, right? This 6 plus 0. So this is not diagonally dominated. in this case, if we have gone through the procedure, so this is the so what I said, this equation is 1, this equation is 2, this equation is 3. The 1 will give you equation of x. So from 1, 2x plus 5y is equal to minus 7, which leads you to 7 minus 7 plus 5y, which leads you to x is equal to minus 7 minus 5y divided by 2. Rather than what we used here, for x we use this equation. Okay, here which will lead you to this. Second equation will lead you to what? 2x plus y plus 6z is equal to 13, right? So if from here you will get a second equation, will give you to equation of y. So 13 minus 2x minus 6z divided by 2. No, that's it. And third equation is 4x plus y minus z is equal to 1. So z is equal to minus 1 plus 4x plus y. So these are the three equation one can write, right? We have seen by swapping the equation, the solution doesn't change, right? But if you, in the iterative method, if you have used this, so you didn't check the diagonal dominance and you just random with these equations you are going to solve. And let's see, so here also what we will do, x of 0 is equal to 0, y of 0 is equal to 1 and z of 0 is equal to 1. That's what is given. And if you have gone for the Gauss Siedel method, what we did, you will end up like this. You can try it at your own time. So you will, first iteration you will get these values. Your error would be something this. Second iteration it would be this. Third iteration it would be this. And if you can see, it is going towards infinity. The x value is keeping on increasing, and error is also getting on increasing steadily, right? So it's, what is the crux of this discussion is, whenever you are using a iterative method, that is a Gauss Siedel, or even in the Jacobi you will see, it's always you have to check for a diagonal dominance. If you don't check that, your solution will never converge. They will always go to the infinity. So when you are using this the Gauss Siedel or a Jacobi method, first you have to check the diagonal domination is there or not. So after this, what we have to do by Jacobi method, right? So first Gauss Siedel method is done. Let's do by Jacobi method. So again, the what is A augmented B, that will not change, right? That is 4 1 minus 1 1 minus 2 5 0 minus 7 2 1 6 30. Okay, so this will not change in Jacobi method. Eventually, your x equation, y equation, and z equation will not change, right? Because this is what we started with. Again, if you check the diagonal dominance, it is there. So diagonal elements are here with the if the summation of the column wise elements are seen. So what was your x1? X1 was 1 minus 1 y plus z divided by 4. Y is minus 7 plus 2x divided by 5, and z is 13 minus 2x minus y divided by 6, right? So in Gauss Siedel what we did, so x0 is 0, y0 is 1, z0 is 1. So Jacobi method iteration 1. Iteration 1 for this thing. So x1 is 1, minus y would be y naught, z would be 1 divided by 4. This is 0.25. Now for y1, what we did in the Jacobi method, in Jacobi method this is minus 7 plus 2 into this x we considered as a 1, right, and solved. So we substituted this value here in Gauss Jacobi method, Gauss Siedel method. In Jacobi method, you will not consider this the latest value. We will always consider the x, y, z value of the previous iteration in Jacobi method. So here you will consider this value, not you will consider this 0 value, not 0.25. So here you will have a 0 only. So this is minus 7.5. That is minus 1.4. Right? Now Z1. Sir, what would be Z1? Z1 would be 13 minus 2 into what will the x value, sir?
0.
0, and the y value would be 1 and divided by 6. So this will lead you to 2. 12 divided by 6 is 2. So right, so if you see error is epsilon x is 0.25 minus 0 divided by 0.25 is equal to 1. Epsilon y would be minus 1.4 minus 1 divided by minus 1.4. .71. Epsilon z would be what, 2 minus 1 divided by 2, that is 0.5. So here again the starting error is very high and they are far off, x value is far off from, so actual value is what, 1, for y it should be minus 1 and for z it should be 2. So this is nearby, that is why error is also less, but these two values are far off. So again you will have to iterate it and then get to the solution. So if you do it, you will you can do it at your mean time. So at your free time. So if you do it using a Jacobi method, so that this iteration we did 0.25 minus 0.142, and these are the epsilon values we got, and you keep repeating it, then at 8th iteration your error in the for x, y and z, it goes in the range of 10 raised to minus 3. For that you are getting the actual value. So this is 1, this can be considered as a minus 1, and this can be considered as a 2. So you are technically getting, even if you keep on repeating, there is a marginal difference. So here you are getting minus 1, 2 and 1 at a 16th iteration. So it's futile activity to go from 18 to 16 just to get this much of accuracy. So what you can say is, while doing the analysis, or you will say is, so in exam also they will say, do it till the accuracy becomes 10 raised to minus 3, or accurate 3 decimal places. So accurate 3 decimal places is this. Okay. So this is for a diagonal dominance, where we considered at the start, while writing down the equations, we considered the diagonal dominance and then converted into the XYZ equations.
So which method will get more accurate? Either it is Gauss Siedel or Jacobi. With early will get,
with both you will get accurate answers, but Gauss Siedel will converge. Gauss Siedel will converge faster most of the times. I'm again saying most of the times.
Step 5 and this is step 8.
Sorry.
Gauss Siedel is taken within 5 steps.
Yeah.
Jacobian taken up to 8 steps. Iteratives.
So can you tell me why? Like why did that happen?
Same, that is the previous values what you are taking.
Yeah, so in Gauss Siedel what he is doing is, he is taking the latest value of x and calculating latest value of the variable and calculating the remaining variable. In here what he is doing, he is considering explicit the value of the previous one. That is why it is converging in the lesser time.
Okay.
Okay. So you with both you will get the accurate solution. It depends on what you use. That's it. Even again, if you have not did the diagonal dominance and just directly have got down the equations and solved it using the Jacobi, again the values wouldn't have converged. So they are keep on going to infinity. So 10 raised to 10. So this is just absurd. So you have to be cautious with what, while doing it, you have to always first check diagonal dominance. And there is a little difference between a diagonal dominance and what we do for a row exchange, that is we select the diagonal element that is very high in the magnitude. Here we are checking the summation of the rest of the elements and getting comparing with the diagonal element. So there are subtle differences that you can note down or keep in your mind. So the final equation is this. So we'll see this quickly. So again, this point you can solve this one, right? Or I'll have to go through this also.
Same, that is A11 x1, A12 2x2.
So what the first step would be? This is Thomas algorithm.
Row multiply with columns.
Sorry?
Row multiply with columns and is equal to 41. First row
but you have to solve. You have to get the value. You have to solve, right? So you have to solve for x1, x2, x3, and using Thomas algorithm. So what will be the first step in Thomas algorithm?
0.8 into x1 plus minus 0.4 into x2 plus 0 into x3 is equal to 41.
Why you will do that? You will have to first write the augmented matrix, right? That's what you are saying. First you will write this matrix, that A augmented B, right? Thomas algorithm, first you will have to start with this 0.8 minus 0.4 0 41 minus 4 0.8 minus 0.4 25 0 minus 0.4 0.8 105 Now again, if you see this one, and this one, this is 0, this is 0. This element and this element is same. This element is same. This element is same. So this is a tridiagonal matrix. Hence we can use Thomas algorithm. Right? So in Thomas algorithm, first what we do, we make the diagonal element 1. So R1 would be R1 divided by 0.8. So this is 1, this is 0.4 minus 4 is equal to minus 0.5. This would become 0. 14 divided by 0.8, 14 divided by 0.8 is 51.25. This row will remain same. These two. Now what you will do, using this 1, you will make this 0. This is already 0. So R2 would be R2 plus 0.4 R1. So 1 minus 0.5, 0, 51.25, this is 0. This would be 0.6. This will remain as it is because R1 into R1 is 0. So this is 0. R2 would be same value. 25 plus 0.4 into 51.25. That is 45.5. R3 will remain same. Right? Now again we'll go to this one because these two values are 0. So we are done with the first pivot. Second pivot, in our second pivot we will make it 1. So R2 would be R2 divided by 0.6. Right? So that would be like 1, 0, 0.5, 0, 51.25, 0, 1, minus 0.4 divided by 0.6. So that is 0.6667 2 by 3. And this one would be 45.5 divided by 0.6. This is 0, this is 1.4, 0.8, 105. What you will do, using this one, you will make a 0 here. So R3 would be again R3 plus 0.4 R2. That will give you what? 1 minus 0.5, 0, 51.25, 0, 1 minus 0.6667, 75.8333, 0, 0. This will become 0.8 plus 0.4 into minus 0.6667. R2 is .5333. Right? Correct now? R3 is what? 105.4 into this is what? 75.8333. 135.3332. So we are below this, there is nothing, or you can do the one step ahead if you want to do that. Then what we can do is R3 would be R3 divided by 0.5333. So 1 minus 0.50, 51.25, 0, 1 minus 0.667, 70.833, 0, 0, 1, and this would be 253.76. So therefore back substitution. So we are talking within the terms of what? X, Y, Z, or X1, X1, X2, X3, right? X1, X2, X3. So X3 would be 253.76. X2 would be 75.833 plus 0.667 into 253.76. X2 would be 245.018. So this is X3, X2, X1 would be 51.25 plus 0.5 into 245.018 minus 253.76. Correct? Hello?
It is not compulsory to positive or negative any value, no, sir. Satisfy the equation.
Yeah, it just satisfied the equation.
But it should be go for tri-diagonal matrix for Thomas rules.
Yeah, tridiagonal matrix should be the condition. So tridiagonal matrix is like you have to have a diagonal element, super diagonal element, and subdiagonal element, and these two values should be similar, these two values should be similar, and the rest of the values should be 0. Okay, so that will leave you to the Thomas algorithm.
Sir, uploading for these videos will upload immediately, otherwise it will take some time.
Maybe tomorrow
Because
evening,
today,
by
12
tomorrow
o'clock,
evening,
we have to submit assignment. At least re-verify if you uploaded immediately.
I'll do it today. Tonight I'll do it. Tonight.
Because 12 o'clock, we have to submit assignment. Cross verification for steps.
Oh, okay. I'll submit it. The last date is today or tomorrow?
Today Friday, Wednesday. Because yesterday one day we skipped, you know.
Okay.
Today is the assignment resubmission date, deadline 12 o'clock.
Okay. So I'll do it because it takes some time. It's a YouTube video, right? So it takes some time. I'll try my best. So I'll do it as it's over. I'll upload it.
Immediately, please upload it.
Yeah.
We'll class verify for us to refer.
Okay. I'll do it. Don't worry. So maybe so these are the all I wanted to discuss for the today. Maybe I'll just go through the recap if you want. So we are completing linear algebra here. So linear algebra topic is linear system equations. Topic we are completed today. So first we started with the basics of linear algebra. What are the addition, subtraction, and all those things. Then we saw system graphical representation, and then we discussed about what is the rank of the matrix is and how it gives you nature of the solution from the rank. Then we direct methods. We saw some direct methods for solution. So in that first one is a Cramer's rule. Second one is Gauss elimination. That is a naive Gauss elimination. Third one is Gauss-Jordan method we saw. Then what we saw? Then we saw the LU decomposition. So LU decomposition can be used to find out the inverse of matrix, right? Then today we saw Gauss elimination with partial pivoting. So we saw what is a partial pivoting. We will check in that column, pivot column, what is the highest value, and we will swap that highest value to the pivot position. Then we saw why we do that. Also we saw how it reduces, how it removes the problems related to numerical analysis, how it makes it numerically strong. That we saw today. Then what we saw, Gauss elimination, then Gauss-Jordan, Gauss elimination. Then we're done with, no, there is a for tridiagonal matrix algorithm, TDMA, that is Thomas algorithm we saw for tridiagonal matrix. So your system of equations can be repetitive and there is some form to it. So if you come to that tridiagonal matrix form, it's better to use a TDMA. Then we are done with direct methods. After direct methods, what we saw is iterative methods. So in iterative method there are two methods, Gauss Siedel and Jacobi. Right? In Gauss Siedel, latest value is used. So whatever the value of x, the latest you have, you use it for the next iteration. Here, previous iteration values are used. So all values of x, y, z, even if you get the value of a y latest and you're calculating for a z and there is a value of a y to be put inside the z, you will not use the latest value, you will use the value that is in the previous iteration. So that is the only difference. Both of them will converge provided you keep the track of diagonal dominance. So you have to first check the diagonal dominance of the matrix. Are the addition of the columns, a column element are greater, are the less than the pivot element, then you will have to shift them. Yeah. So I was talking about iterative method. In a Gauss Siedel method, in a Gauss Siedel method, you will always use the latest value of x, y, and z. And in Jacobi method, you for the first, second iteration, the x, y, z values you will use of the previous iteration. Even if you get the x, y value in the current iteration, you will not use them. So that is the only difference. And for a Gauss Siedel or Jacobi to converge, you will have to check the diagonal dominance.
Maybe signal problem.
Yeah. So just that you have to check the diagonal dominance and you will be good to go with this equation. So if you have any doubts, please post them on the Google forum and I will address them as and when I get the time. And even professor also check those forums. So even if you have any doubts, you can directly ask him there also. So thank you from my side. If you have any doubts, please post them and try to come to the live sessions.
Thank you.
Okay. See you soon. Good night.